Okay.
I would love to see it. Yeah, I think he's you found him. But who are you talking about? Who are you talking about? He is.
Okay, covalent bonds. Remind your partner what type of elements are involved in ionic bonds. Yes. Metal plus nonmetal. And when the metal becomes an ion, what is its charge? Tell your partner, what's the charge on a metal? Charge on a metal. It is positive. That means that nonmetals must be negative. Isn't that nice that nonmetal and negative both start with the letter N? All right, so that is ionic bonds. We have a metal and a metal, but when we're dealing with covalent bonds, what kinds of elements are we looking at for covalent bonds? Nonmetal plus nonmetal. So over here on the right, we have a picture of two atoms. And I would like you to see if you can figure out which element those atoms are. Which element are those atoms? Yes. There you go. Jade? Hydrogen. How do we know that? Because it has one proton and it has one electron. So we have a hydrogen atom and we have a hydrogen atom. How many electrons is full for the first shell? 2 electrons is a full first shell. So 2 electrons is a full first shell. Does hydrogen have a full first shell? No. So what I would like you to do is I would like you to look and see how does hydrogen fix that problem? How does hydrogen fix the problem of having only 1 electron in its outer shell? They share. So we have a pair of shared electrons. Now, what do you know about positive charges and negative charges? Positive and negative attract. So positive attracts negative. So this positive nucleus here will attract the shared electron. It will also attract to the other shared electron. So that's like a force between those two? Does anyone know the name of the force? Some people who've been working ahead might know the name of the force that we have between positive and negative charges. Yes? It's called an electrostatic force. That doesn't look like an RO. I'm going to try that again. So any force between charges is an electrostatic force. And we not only get those between the nucleus on the left and the electrons, but also between the nucleus on the right and those electrons. So we are going to do a little play acting here, okay? So each person needs a pen or a pencil in their hand. One pen or pencil in their hand. Okay? Now, we are going to, and I'm going to find someone who doesn't have a, Zidane, could you volunteer to come up here and be my partner for just a moment? Okay, we'll just kind of meet here in the middle. Bring a pen. Yeah, fine. So, I'm non-metal, let's say I'm hydrogen. Here's my one electron. Zidane is also hydrogen, and he has one electron. Yes? Are either of these happy at this point? No. How could we fill up our shells? We could share. Okay, so I'm going to hold on to that one, and you're going to hold on to that one, and I'm going to hold on to this one, and you're going to hold on to that one. Now remember, the nucleus part is positive, right? And the electrons are negative. Nucleus positive, electrons negative. What does positive do with negative? It attracts, so it pulls on it. Okay? And you can't see the force, but, right? Like, I mean, I can, you know, you can see we're both pulling on these. All right? So I want you to do the same thing so you can feel what a covalent bond feels like. Okay? So find a partner. Thank you so much, Sinan. If you don't have a partner,
It's too small for shaking that big. But you just grab him. Oh, you know what? Oh, I'm gonna give you a couple pens. It's too small. Oh, yeah. One, four, please.
like they must have come out yesterday, I think. Yeah. Yeah. Okay. Next job, you're going to work with the same partner again, so you guys can just stay, okay? And the person on the left is going to be the metal. The person on the right is going to be the non-metal, because that's how our periodic table goes. Left is the metals, right is the non-metal. So each of you, once again, are going to have one pen. Okay, one pen. And I would like you to see if you can figure out what ionic bonding would look like if the person on the left is the metal And the person on the right is the non-metal. When you think you've got it, call me over and I'll take a look and see it. So, metal on the left, non-metal on the right. See if you can figure out what to do.
And now I pull
Call me if you think you got it.
Wait, is it not
Okay, so you are
Yes.
you.
I know positive.
Those are you. So you're negative and what's possible? Okay.
I'm positive.
Okay, why do you only have one off? Yeah, yes, the metal should be the left hand. Okay. Brian. Crochet. You're the tinker.
Exactly, it's all in the head. John, you. Hey. John, hey. Anybody go?
Alright, if you give me my stuff, I'll give you a water bottle and your pencil. That's not a video. No, I said dog. What? Dog. Oh, I'm sorry. Give it a electron and then. Hey, stop. Dude, that's too much. Yes. You know what? That's a point. You want that?
Yeah.
Everything. I'm ready. You have these. You have the water.
Fair share. What about mine? Okay.
Okay.
Give me my book.
Alrighty. Did anybody not get a chance to show me? I think everyone did. Go sit down. Go sit down and stop talking. Go. Sit down. Stop talking. Go, go, go. Okay. Shh. Okay. We can also show this as the electron cloud model. You're not responsible for drawing the electron cloud model. Okay. And this is just a nicer picture of the attraction and the shared electrons. Okay, next page. You do not need to know this unless you're interested in the enriched stuff. Non-metals all have similar electronegativities. And remember, electronegativities is how much they like to pull on electrons. So do you remember when you were covalently bonding, both of you were pulling on those electrons equally, right? So that's why you end up sharing. But when you were ionically bonding, one of you was like, here, have this electron. And the other one was like, I'm going to keep them. They're all mine. They're all mine. Yes? So I actually don't love this page, but we'll do a little bit on here anyway. I feel like I need to edit this. I don't really know what I did to my throat there just a minute ago, but it's going crazy. Hydrogen. How many holes are in the outer shell of this hydrogen atom? How many holes are in the outer shell of this hydrogen atom? There's one hole. Okay, here we go. How many holes in the other shell of the hydrogen atom? One. Okay, perfect. Now, if you have one hole, you can form one bond. So look at this. When these two guys come together, we have one pair of shared electrons. How many bonds is one pair? It's just one. A pair of electrons equals one bond. So we have one pair of shared electrons, and so one pair of electrons is equal to one bond. So if we needed to draw this, we would draw an H, and then we show a single bond by drawing a single line, and then drawing an H. How many electrons in that line? 2. Is good? How would you write the formula for that molecule? You would write H2. Just like that, right? No. Why not? What have I done wrong? What is wrong with this H2? Yes?
2 goes on the bottom.
The 2 goes on the bottom, not on the top. That's right. And in fact, we're going to draw fluorine down here. We're going to draw F2. And the reason it has to go at the bottom is because this is a sub, which means below, script, writing. Okay, and that's why it has to go below the writing, because it is a subscript. All right, fluorine. Now, one thing I'd like you to notice about fluorine is that normally, when we draw a Bohr model of fluorine, how many shells would we draw? We would normally draw 2 shells. Now, I don't know if you remember, but fluorine is in row 2. In other words, it is in period 2. And therefore, it is going to have 2 occupied shells, okay? Yes, of course. So if I was to say, okay, let's not talk about fluorine, let's talk about chlorine. Let's just go over here. So this is row 1, row 2, row 3. In other words, period 1, period 2, period 3. How many occupied shells would chlorine have? It would have 3. And if you've forgotten why, let's just bop back here for a minute, okay? And we'll just take a look at this really quickly in case you have forgotten. So if we look at the Bohr models for period 1, hydrogen has electrons. It's only got 1 shell with electrons in it, yes? How many shells does helium have with electrons in it? Just 1. And then when we get to the end of that row, that shell is full. Yes? Then we come to lithium, and lithium has its first shell, but it also has a second shell. Okay, and as we go across, we always have how many shells? 2 shells all the way across that row, and you'll notice, what are we doing to that shell every time we move over to the next atom? Every time we go to the next atom, we are adding 1 more electron. And so we have 1 electron, 2 electrons, 3, 4, 5, 6, 7, and then we are full. And when we get full, we have to start a new shell, which means we also start a new period, a new row. Okay? So one of the things that's going to be really handy is that when we're bonding, do you guys find it a bit of a pain in the butt to draw all the electrons in a Bohr model? A little bit of a pain? Okay, if you're drawing like 20 electrons, it's a bit of a pain. So the nice thing is, often when we are bonding, we will only draw the valence shell. Okay? Often we draw only the valence shell for bonding. Because the other electrons aren't involved in the bonding anyway, so why bother with them? Yes? So we just, even though fluorine technically would have an inner shell with 2 electrons, we are just going to ignore that because they're not involved in the bonding, so we don't have to draw them. Now, if you have trouble figuring out that fluorine has 7 electrons in its outer shell without drawing the whole thing, then by all means draw the entire thing, okay? Not a problem, it's just a little bit more work for you, okay? But if you find it easy to know that fluorine has 7 electrons, then in its outer shell, you can just draw 7 electrons in the outer shell. How can you tell from your periodic table that fluorine has 7 electrons in its outer shell? Tell your partner. How can we tell that fluorine has 7 electrons in its outer shell?
What is it again? Oh.
So how do we know that fluorine has 7, Jade? It is in group 17, so we ignore the 1 and we just look at the 7 and we say fluorine has 7 valence electrons. So how many valence electrons would we have if we were chlorine? 7. And guess what? You can go all the way down the halogens, even all the way down to astatine. How many valence electrons in astatine? 7, because it is in group 17. How many valence electrons in carbon? 4, because it is in group 14. Okay? Now, I know some of you know this already, but if you haven't picked up on it yet, this is a super easy way of drawing your valence shell. So this has 4 valence electrons. So if we went down to germanium, how many valence electrons in germanium? 4. How many in gallium? 3, because it is in group 13. Okay? So that is really nice way of telling who has how many valence electrons. All right, back to here. How many holes do each of the fluorine atoms have? How many holes in their outer shell? I should really unlock this door. This is really awkward. I locked it. How many empty spots? 1. We got 1 here in this fluorine atom. We have 1 here in this fluorine atom. What does that tell you about the number of bonds each fluorine atom can form? 1 hole. Therefore, we're going to get 1 bond. Okay? So these guys now overlap with one another. We have 1 pair of electrons. How many bonds is 1 pair? That is 1 bond. Okay. here we have carbon, and carbon has 1, 2, 3, 4 electrons in its valence shell. What group must it be in? 14. Okay. How many holes or empty spots are there in the outer shell of the carbon atom? 4. 1, 2, 3, 4. So how many bonds? 4 holes. Therefore, carbon can form how many bonds? 4 bonds. Okay? And it needs to form 4 bonds in order to fill up its shell. Okay? Now, oxygen. I know the structure's drawn a little bit weird, but let's just go with it for now. Okay? Oxygen has 6 valence electrons. So how many holes does it have right now? It has 2 holes. Okay? So how many bonds can oxygen form? 2 holes, therefore 2 bonds. And in fact, it needs to form 2 bonds in order to fill up its shell. Yes, for sure. So what we're going to see over on the right is that carbon, you can see carbon's electrons are shown in yellow here. Okay, I'm going to go over them in red just to kind of, make it an active process. So there's my 4 electrons from carbon, and each oxygen atom has to share 2 of its electrons. So maybe these 2 are here, yes, and then these 2 are here, or something like that. No, I've done it wrong. Oh, it's because there's no other oxygen atoms shown. Okay, never mind. Now, let's take a look here. How many pairs of shared electrons? We have 2 pairs of shared electrons. So how many bonds is that? 2 pairs is 2 bonds. So if we were to draw a carbon dioxide molecule, we would put the carbon in the middle. We would put an oxygen on either side. And what would we attach the oxygens to the carbon with? 2 lines. So we have a double bond and a double bond. Okay, so that's a double bond. It's 4 electrons. It's 2 pairs of electrons. Carbon used to have only 1, 2, 3, 4 electrons. How many electrons does carbon have now, given that it's sharing a whole bunch? It's got 1, 2, 3, 4, 5, 6, 7, 8 electrons. How many did it want? 8. Great. How many does each oxygen have now? It's got 2, 4, and then the 2 shared pairs make 8. Okay, so everybody now has 8 electrons and everybody is full. Okay, and you can see here we have carbon tetrafluoride. Because we have 1 hole in the fluorine, it can only form 1 bond. We have 4 holes in the carbon, so it can form how many bonds? 4 bonds. All right, and so how many fluorines do you need to form bonds with the carbon? You need 4 of them because fluorine can only form 1 bond and carbon needs 4 bonds. So we need to have 4 fluorines. And so you can see we have 1, 2, 3, 4 bonds, each being fulfilled by 1 fluorine. This molecule is called carbon tetrafluoride. Can you guess what tetra means? Tetra means 4. And in Unit 4, we'll learn what those prefixes mean. It's just like carbon dioxide. Di means 2. Okay? Now, if we need to write the formula for this, we don't have a metal, but we're still going to read left to right across our periodic table. Who is first if we read left to right? Is fluorine first or is carbon first on our periodic table? We're reading left to right. Look on your periodic table or look on a periodic table. Carbon is first and then fluorine is second. So we will write the formula as CF. And do I need to add anything else to that? I need to add a 4. No? Why not? It needs to go at the bottom. And what, do I write a 1 here? No, why not? Because we just don't, right? If there's just 1, we just leave it blank. Yes. Yeah. Okay. So here's a definition of a molecule. A molecule is, and we're going to highlight these various things, it is electrically neutral. It is a group of 2 or more atoms. And those atoms have to be nonmetals. And they are held together by, oh, I don't like any of my other color options. Oh, really? That's it? Okay. Ooh, let's try that one. See if it'll let me do that. Held together by covalent bonds. Look, it's a pretty purple color. Oh, that's so exciting. Too many menu clicks, though, to get to that on a regular basis. Okay. So now we have defined the term molecule. Why does a formula unit not qualify as a molecule? In order to answer that, you need to know what a formula unit is. Please tell your partner what is a formula unit. Please describe to your partner. Why does a formula unit not qualify as a molecule? Or actually, before we do that, we need to say, what is a formula unit? What is a formula unit? Sorry. What is a formula unit? It's a single unit of an... Yes? Ionic compound. That's okay. So it is a single unit of an ionic compound. And could you draw a picture of a formula unit? Yes? Do it right under where you wrote formula unit. Draw a little picture down here somewhere of a formula unit. Today's not Friday, is it? Oh. I need a weekend. And I'm sure you do too. That's okay. I get to go home and I get to fix my dryer tonight. It stopped heating over the weekend. So I tore it all apart. And then I'm like, okay, I figured out what was wrong. I'm like, I need this part. And I'm like, oh, shoot, nothing's open because it was like Monday, the holiday, right? So I'm like, okay, fine. So I got them to, I sent an order to Reliable Parts in Coquitlam. And then they sent me an email, but my Wi-Fi was turned off, so I didn't get the email. And so I didn't pick it up on Tuesday. And then Wednesday was the staff meeting, and they closed at 4:30, and the meeting didn't end till 4:30. So I've been without a dryer for 3 days. Thank God it's only me at home. My husband is away, so it's okay. We're living without a dryer. So I have to go after school today and pick up the part and finish fixing the dryer and get all the parts of the dryer that are out in my living room out of my living. Oh my God. Too exciting. It's wonderful being an adult. So awesome. Although I have to say, fixing your own dryer feels really good. Like if you get a chance to like fix something, you should try it. Like if your dishwasher isn't working and it has an error code, like go online and watch the YouTube video, right? Because this is how we do things, we adults. I don't know what people did before YouTube. My dad just seemed to know how to do everything, but I go onto YouTube and I'm like, okay, it has error code 24. How do I fix that? And it tells you, and you can go do it. It's very exciting. You should try it. Try it. Okay, sorry, I got all excited about that. Formula unit looks like that. If you're really concerned, yes, the positive ion is usually smaller than the negative ion, but your guys are in grade 9, so I don't care if you get it backwards, okay? So if you're concerned, if you're interested in that kind of thing, the cations are smaller. If you want to talk to me about why, you can stop by after school or during flex. Otherwise, you can just not worry about it, okay? Yes? Huh? Yes, yes. So this is not the only formula unit, but it's enough for this question. Okay, we'll go more tomorrow into what other formula units look like. Yes? Cool. Okay, so it's a single unit of an ionic compound. It looks like that. Why does a formula unit then not qualify? Oh, by the way, what type of element is this positive one? That's a metal. And what kind of element is this negative one? Non-metal. So why is a formula unit not a molecule? Baran, I'm going to get one from you. Okay, okay. Number one, molecule is made of non-metals, and guess what we have here? We have a metal. There is a second reason. Milan, did you have a second reason? No? Okay. John, you look like you're dying to give me a second reason.
It's like formula units made of ions, but like the molecule is made of neutral atoms.
Yes, yes, absolutely. So the non-metal is held together by covalent bonds. Yes. The formula unit, which I cannot abbreviate because it's rude, is held together by ionic bonds. Whereas a molecule is covalent bonds. Is good? Yes. Now on the next page, there's like a whole rambling thing about it, which you can read if you want to. Okay. But we're going to skip over that because I want to get done. In fact, I'm dying to get out of chemistry. And we have one more unit in chemistry. So we may cut this one off before it's time. And we may make anything that we don't cover like an enriched kind of thing. Yes? Okay. So because I think we'll be okay without it. And I think it'll all be fine. It'll be fine. Why does a formula unit not qualify as a molecule? Because it's made of ions, it contains metal and non-metal, it has ionic bonding, it's made of oppositely charged ions, not neutral molecules, and a formula unit never exists on its own. A molecule can exist on its own. All right. Do you think that seeing this structure here, we are now on page 47, page 47. Do you think you could draw the molecule that forms from carbon and 4 hydrogens? Do you think you could finish that up over here? Do you think you could take these 5 atoms and turn it into a molecule? Do you want to try? Yeah. Give it a try. Could you write the formula for this thing? And here's like a little tip. Hydrogen is weird. Hydrogen usually goes at the end of a formula. Well, in this case, it does. Hydrogen often goes at the end of a formula. Not always, because obviously H2O. But if I were to tell you in this case it does, could you write the formula for this compound? Yes. Yes. Formula would be CH subscript 4. Is good? Okay. N is here. And how many holes are in the N atom's valence shell? 3. So how many hydrogens will you need to fill that up? 3. Could you draw the molecule formed by nitrogen and 3 hydrogens? Why did I put N's in the middle of those? Those should have been H's. Oopsie. La la la. There we go. And our formula for this one, again, the hydrogen goes at the end. It would be NH3. And if you're interested in knowing the names of these compounds, there are some of the compounds that are really common, sometimes go by non-standard names, okay? The standard name for NH3 would be nitrogen. Can you guess what we'd put in front of hydride? Nitrogen something hydride. Any guesses? Remember, CO2 is carbon dioxide. Can you guess what it would be? It would be nitrogen trihydride. But sadly, this is a really common compound, so we don't give it its sort of standard name that's easy to figure out once you know the rules. And don't worry if you're like, I don't know the rules. Unit 4 is all about the rules, okay? This is actually ammonia. Have you heard of ammonia? It's in a lot of cleaning products. So if you have Windex, it's got ammonia in it. Lots of like glass cleaners and especially have ammonia in them. Now, CH4, once again, if we went by standard naming practices, we would call it carbon something hydride. And I don't expect you to actually know the one for 4. It sounds like you would expect it to be quad maybe, but it's actually tetra. Tetra means 4. Yeah, we did that earlier. Tetra is 4. Now, but we don't actually call this carbon tetrahydride. It's actually known as methane. Have you heard of methane? Yes. What is methane famous for? Cows. What do cows do? They burp and they fart. And what comes out of cow burps and cow farts? Greenhouse gases, and methane is a greenhouse gas. Yeah, one of the gas giants, I think, has mostly methane. Now, the gas that comes out of these gas taps is methane gas. The reason it smells funny is because they add something to it. to make it smell funny so that you'll know if the gas is on. Why do we have these? So we can use Bunsen burgers, which we will do at some point in the future.
Why we used one last year?
If I get my act together next week, we will use the Bunsen burgers next week.
I think we used one last year. That's when Damien burned the start.
I hope so, yeah. I hope so.
I went to the project with Damien, and then he put it on the hot plate, the styrofoam, and it started burning. Apparently it's toxic.
And then get the
Damien,
dissecting
that's one of the times we got.
and all those
Only
things.
one of the times.
Yes.
The other time,
Yes.
probably when he was.
I figured out where to go buy them, because last time I did this, I did not have to buy them myself. I don't know. And then do I get reimbursed for them? I don't, it's just, there's a lot of layers to it. And mostly when I go home, I just want to fall asleep. So, you know, anyway, but I will try to snap myself out of that so you guys can have a nice dissecting flower experience. All right. La 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 la. You guys are going to now do, most of the rest of this is like enriched stuff, so you can like not do it if you don't want to. Page 53 and 54, omit number 7, because we've not covered that yet. So that's your homework, 53 and 54. Wow, I recorded that lecture today with me talking about my home appliance repair and cows farting. I don't know. Stop